I'm the only one that's excited.
No, this is exciting. I am super happy.
No, I was excited.
It's awesome. I'm just gonna go, boo, you're wrong. Boo. The shovel's on the ball. Did you feel that?
I remember her when she was just a brand.
That was a year and a half ago.
It feels like much longer, doesn't it? It's like, yes.
A little bit, yeah.
They're still using Kate's photograph on University of Wisconsin-Madison website.
Mm-hmm. I keep getting emails. We're in the newsletter.
With you?
We asked permission
For
though.
the stream.
You did
So
that.
that will have to
Yeah. I'm not sure how these things work.
Nothing to see here.
Both my like one of the
Memorial Day.
Yes.
yeah, of course. Before you pay for it to come back,
Starting-
take it back.
The project that I ended up with a position on was too good to say now. It's fire and carbon service, but it's in Alaska.
Oh, well, it's university.
So it was just a really
So the people in front.
Yeah.
Right, yeah.
Yeah, so I fly out
Looking behind you.
to Fairbanks, Alaska on the day. And then I'm there for about a month.
Higher education, one thing.
I'll actually be on the ski program. The PhD advisor that I'm working, he actually got a job offer. So rather than being Fairbanks year-round.
This is bad.
Yes, yeah. I was kind of, I braced myself for Alaska.
Everyone just becomes very surprised. I'm not even sure what something
You know,
Yeah, no. I don't think so. I'm trying to broadcast it, and I think I just.
Yeah.
We had the
I haven't been here for.
so this is Bill's and they already, I mean, they know who it is, but they said, but thinking about Bill's experience and how that helped him. I don't know if one of the like really in the first year.
Yeah.
I'm gonna ask a really important question.
That's kind of.
Yeah, but it's most of them are, you visit like yes.
Wow.
Yeah, and I actually ran out of my.
I would say no to that. I would say
Oh, there's a type of this.
You're off.
The last thing. I'm live streaming, I guess.
You did do it, but. Yeah, that's. All my stuff. Yeah.
That's like, I'm so serious. How about we do Star Wars gaming?
We didn't even answer.
I got people that fall into we'll have safety. Yeah. Makes it funny to find you happening.
What's the?
Real exciting.
Thanks everyone for coming to Kate's presentation. Hooray. Just a few words to introduce Kate, who I don't think I need to introduce her really, but you know that she's been a great member of the department, helping out with so many aspects of grad life and university life also. But she's also been a great member of our lab, just with our little cohort crammed into that corner room in Columbia for the last year while, while we didn't have a lab to work in. And so she's had to deal with lots of adversities, especially the stuff I kept throwing at her, like, I want you to use this method I've never used before and tell me how it works, which is what she did. So, which involved buying equipment piecemeal and then getting the whole thing operating and going. Yeah, but then the real challenge, of course, was tell us about fire history in redwood forests, where there's just no information except there is a problem because we know that they burn, but don't know really anything about their history. So she also had a really complex thesis question to work on as well. So we're sad to see you go, and I don't even count the days anymore because it's like pretty soon. Yeah. So we'll let you take it from here.
Awesome. Thank you. So thank you all for coming. I'm really excited to be able to share the work I've done in my time here. And I also wanted to take this chance to just say thank you all for a really lovely 2 years. I've really enjoyed my time here, and I'm really grateful to be a part of this community. So I'm going to talk to you today about fire and carbon cycling in redwood forests. And there's a lot of kind of interesting stories here, so I'm excited to share those. So fire is an important ecological process across a wide variety of ecosystems globally. It affects things like forest structure and composition, and the impacts of the scale of the impacts of fire range from anywhere from sort of microbial impacts on soil systems to landscape-wide changes in species distribution and other biogeographic factors. But the role to which fire influences or interacts with coast redwood forests specifically remains a bit unclear, and there's a couple of reasons for that. So first off, these are really wet forests. Oh, thank you, Bart. That'll make the pictures better. So if you've been to Redwoods National Park, if you've watched the third Star Wars movie, this is even better, I can't see it. These are, no, this is great. Yeah, this is fine. This is actually what a redwood forest looks like.
Oh, here.
It's on the
Yeah,
side.
right here.
Perfect.
Okay.
But it's immersive.
Okay, sorry.
Good here? No worries. So these are wet forests. And the precipitation regime in here is pretty intense. You have winter rain that starts about September, goes until June, and then you have summer fog that kicks in June and goes until about August. And so for a very long time, it was presumed that that wetness would exclude any sort of prior fire frequency, fire pattern, any sort of fire regime, really. But the conundrum here is there is fire in redwood ecosystems. We have physical evidence of it. We have tree yearing records that show intervals of 30 years to 5 years to 500 years. So obviously fire is happening, but the ways in which it happens and the impacts of it happening are somewhat uncertain. Two other elements of this story that are really important to mention are ignition sources. So lightning is a really relatively rare phenomenon on the coast of California, which would eliminate any sort of regular pattern of natural ignition source for fire. And the human sort of source of ignition story is also a bit complicated. Cultural and archaeological evidence suggests that the livelihoods of the First Nations people and Native Americans that lived here were really based on things like fishing and trading. And as a lot of the archaeologists in the audience would know, tribes that tend to burn the environment usually do so for agricultural or hunting reasons. So we don't really have a narrative that lines up with the idea of there being fire here. But part of the issue is that in the 30s and the 40s, a lot of scientists just sort of declared that Native Americans did not burn the redwoods, but their argument was less on this sort of livelihood story and was more around the idea that, these populations couldn't have had the numbers or the agency to actually impact their environment in any sort of significant way. So that was just sort of ignored, and we didn't really ever revisit it. So the element of native burning and First Nations burning is kind of unexplored. And I'll try to do that a little later in this talk. And so these attitudes led pretty much directly to a fire suppression policy that lingered for about 70 years. This is Emmanuel, our friend Emmanuel. He's declaring that there's no role of fire in redwoods. And one kind of quick aside is that this is really a production-oriented attitude. It's not an ecosystem function-oriented attitude. He's more concerned with protecting virgin redwoods so that we can cut them down later, rather than understand how they function. And so this really has lingered in a lot of places, and it's important for a variety of reasons. As a lot of us found out last summer, kind of viscerally, the intensity and the frequency of forest fires in the western United States is really increasing. And that's pretty much unavoidable, right? It's due to climatic warming, and it's also due to this idea that we've suppressed fires across the western United States for sometimes hundreds of years. And that's led to quite a lot of fuel buildup. And so now when we do have fires, and whether it's a human or a natural ignition source, whether it's a firecracker from a 15-year-old or it's lightning, it goes up in pretty catastrophic ways. And so the redwoods are not excluded from this. And so understanding how fire suppression policy has functioned in redwood forests, what the impacts of that are really important for being able to adapt our management techniques to the current situation. And so there is fire in coast redwood ecosystems. There's fire in modern times, and there's fire beyond our sort of collective historical memory. This is one example. This is the 2003 Canoe Fire. It burned about 11,000 acres in Humboldt County. And I bring this up not because this has any relevance to my research, but because I needed a picture of fire in redwoods for my slides, and this is the only example that comes up. This is pretty much one of the only fires that has occurred in these ecosystems in the last 20 years. So here you go. I'm not going to talk about this again. Fire also occurs in coast redwood ecosystems beyond our collective historical memory, as I've said. This is sort of the main example we have. This is a physical fire scar. It's on a tree. This is Jebediah Smith Park. This is Stout Grove. So this tree is probably 2,000 years old. And while the age of the scar on this tree remains relatively unknown, we definitely know that it predates the establishment of the park. There haven't been fires in Jebediah Smith Park since the park was established. We can also assume that it probably predates European establishment. So this scar is a legacy of a fire regime that has changed since the last time this tree burned. And the ways in which that fire regime has changed and the consequences to redwood forests are something to tease out and are pretty important to tease out. And so in order to really examine fire in redwoods, you have to take a long-term approach. And there's a couple of reasons for that. First and foremost, one individual coast redwood has an average lifespan of about 2,000 years. So that's a time frame that we can't, as scientists, observe in any sort of really meaningful way if we want to understand an ecosystem process. And furthermore, that means that these forests are generally legacies of different climatic and environmental conditions. When these trees started to grow, the climate was different and the environment was different. And so therefore, it's really difficult to sort of observe how they would act in natural conditions when the natural conditions have changed. Another aspect of this is we cut down about 95% of coast redwoods. 95%. So out of all the coast redwoods we have left, only about 5% is old growth. And out of that 5%, that's Redwoods National Park, that's Muir Woods, that's the scenic byway you drive when you drive down to San Francisco from here. And so a lot of that area, while it's protected, it also gets quite a lot of foot traffic, right? It's a really popular tourist industry in the coast of California. So they're not necessarily undisturbed areas of old growth. If you've been to Muir Woods, there's basically no understory. It's all just kind of footpaths and stuff like that. And so the old growth that we do have left, it's a really small sample size, and it's not an uninterrupted sample size. So that's also important. So we need to really look at long-term contexts to understand how fire would function. And there's a couple of ways of doing that in paleoecology. The sort of one of the main approaches is like lake sediment core. You take lake sediment, you look at poly, you look at charcoal, you can trace environmental change. The problem with that here is that there are not a lot of lakes on the coast of California. And you can't really get a lake sediment core without a lake. That's kind of hard to do. Another sort of long-term record of fire is often tree ring records. So a tree ring will record fire scars, and if you cut down that tree or you core that tree, you can examine the rings and you can examine how often fire occurs within that tree's lifespan. There's a couple of issues with that with redwoods. They tend to rot in the middle, making it hard to get any sort of core out. You can't just really cut them down willy-nilly to count the rings. People are annoyed by that. And while we do have some records, the results from those records suggest there's an issue with tree ring records in redwoods specifically. And what I mean by that is the very first sort of tree ring records of fire within redwoods in the 70s and the 90s came back with fire return intervals of about 500 years. So that would suggest a really infrequent fire regime with really intense fires, really catastrophic fires, not occurring very often. But then when we did more of those in the 90s and the 2000s, we came back with fire return intervals of anywhere from 5 to 7 to 30 years. So that's pretty much the opposite. That suggests a really frequent fire regime, kind of lower intensity fires, but fire being a really active agent in shaping redwood forest composition and structure. So we need to resolve that discrepancy. We need to add more information. And my way of suggesting we solve that sort of conundrum is looking at soil, carbon, and charcoal as a potential long-term record of fire, right? If we look at charcoal that's been buried in soil, perhaps we can also use that to compare and to add to the existing information about fire in redwoods across time. Quick aside, I'm using long-term here to refer to basically hundreds to thousands of years. So that's kind of a broad, pun intended, broad term. So you can look at charcoal and carbon in soil and really be able to understand the ages of fires and the ages of fire events for a couple of reasons. So fire is a really important agent in the carbon cycle, and it can contribute to that carbon cycle through two basic kind of fundamental pathways. If you have total combustion of biomass, if something is completely burnt up, it will likely be emitted into the atmosphere as carbon dioxide. If you have partial combustion, if you let your campfire go for long enough, you end up with charcoal or charred material, and if that charred material ends up buried in the soil, it has the capacity for a remarkably long residence time. There's evidence that suggests that charcoal that once it's buried will stay there for thousands and thousands of years. Because there's kind of only two mechanisms that would remove that charcoal. One is bacteria. You can have something come along and eat it, and it'll go away. That's sciencey. And then subsequent fire can actually also remove charcoal, but really only if it's in kind of the top layers of soil. So with that in mind, there's the capacity here to examine soil, charcoal, and carbon as a potential repository, as a physical archive of information about fire, and not only fire, but the impacts of fire. So not only is it important to understand that, okay, we have fire here every 5 years, or every 10 years, or every 15, but what are the impacts of fire? How does fire actually change the environment? What has it contributed? Is it a carbon source? Is it a carbon sink? So understanding the broader implications of fire is also important, and that's information you can get from soil. So I formatted 2 research questions to investigate this sort of element. They're very specific, so I'm going to go over them, but then explain more broadly how they interact with this whole story that I've been telling. So is there a charcoal stratigraphy within mineral soils in old-growth coast redwood forests? Can we use that stratigraphy as a record to contribute to our understanding of fire in coast redwoods, and more broadly, fire in the coast of California? And then secondly, what quantity of soil organic carbon comes from pyrogenic carbon? So how does fire contribute to aspects of carbon sequestration in coast redwood forests? And more broadly, how does fire interact with elements of coast redwood forests across long periods of time? So to do that, I have 2 sort of broad method approaches. The first is radiocarbon dates. This is how we get at the fire history element of this story. So we went out to Northern California, we dug a bunch of holes, and we sampled charcoal directly from those holes and radiocarbon dated those pieces of charcoal. That gives us exact depths, and that gives us ages. So this is how you sort of determine the frequency of fire in the past using a soil archive. This is also going to give us information about stratigraphy, right? So do we have younger dates at shallower depths as we would expect, or is something disturbing the soil? Do we have younger dates buried with older dates at the top? The other element of this study was bulk soil samples. So we took volumetric soil samples from 17 different sites, and we took them in duplicates. And we did that for a specific reason. We used 2 different charcoal quantification methods, as Dan sort of hinted on. we used the traditional charcoal quantification method, which is a physical quantification. And basically what that involves is soaking your soil samples until they disaggregate, putting them through a sieve, picking them out like you're a gold miner, and then hiring an undergrad to count them under a microscope. And as you can imagine, that's really time intensive, that's really labor intensive. You have to get an undergrad, you have to give them podcasts, it's a whole thing. And so newer methods have emerged within the last 10 to 15 years for quantifying charcoal without the sort of time and labor associated with the physical method. And the method we chose to test for the first time in this lab at Oregon was it's kind of colloquially called the KMD test, but it's basically an acid digestion. It's a chemically based method of charcoal quantification. And the way that works is charcoal has what's called a recalcitrant structure. So when something is charred, when something is affected by fire, it forms a really strong carbon structure at almost a molecular level. So you can select for that. If you use an acid, you can use that acid to digest anything that doesn't have that really specifically strong carbon or charcoal structure. So what we did is we ground up our soil samples to a really fine powder. We soaked them in acid overnight and then poured them through a filter to get rid of the acid because no one wants the acid. And then sent those samples along with raw soil samples to an elemental analyzer in Miami. So that'll give us pyrogenic carbon, it'll give us total carbon, and that'll give us sort of an idea of whether this chemically based carbon quantification method is actually more effective than the traditional method that a lot of people have been using. So this is where we sampled. This is the Headwaters Forest Reserve, courtesy of Katy Perry, not the singer. And so this is a forest reserve in Northern California. It's in Humboldt County. It's about 30 minutes outside of Arcata. And this is actually a really interesting site. If we have time afterwards, somebody please ask me about the political history of this place, because it is a great story, but it's not going to fit into this thesis presentation. So we sampled, like I said, about 17 different sites, and we sampled a variety of both mineral soil sites and what we're calling more depositional sites. So the mineral soil sites, you'll see that most of the mineral soil sites on here are actually ridge tops, and there's a reason for that. So we wanted to erase the idea, we wanted to avoid any sort of erosion in our sampling. And what I mean by that is we wanted to make sure that the charcoal we were sampling was in situ. And by in situ, if you sample in a valley and you find charcoal in a valley, there's a chance that that charcoal is actually from the hill next door and not actually from the valley, that it's been eroded in, it's been washed in. But if you sample in a hilltop, ideally you're only getting charcoal from fires that have occurred on that hilltop. So we did that, and we did some valley sites for comparison across a variety of elevations, kind of as far as we could hike up. And so I'm going to start by talking about the results from those radiocarbon dates, and then I'll get into the soil stuff. So from our mineral soil sites, you can see we have quite a lot of ages. We have everywhere from basically modern dates to 4,000 years ago. So already that's pretty significant. Our tree ring record only goes back about 2,000 years because, as I said before, Redwood usually only lives about 2,000 years. Can't really get beyond that. So already our charcoal record from soil is showing us fire histories that extend past existing knowledge of fire in coast-redwood forests, which is pretty significant. You can see most of them, we typically have younger dates at shallower depths, but I'll get into that more in a second. And then for our non-mineral soil sites, we have basically two site types, and I'll describe them a little bit because they're kind of not really clear terms. So the colluvial hollow is a road cut that we sampled. And what you can see is we have much younger dates at shallower depths, and then we have some older dates at deeper depths, and then suddenly we have younger again. So there's obviously some disturbance happening here. There's some soil circulation. But what's really interesting is actually the results from the alluvial fan. So this was a stream bank that we sampled. A stream had cut through and left about 1 meter of soil profile exposed. And I basically climbed into it and sampled it with tweezers. And so we have a piece of charcoal that we found at 10 centimeters, and we have a piece of charcoal that we found at 1 meter down. They're the same age, which is crazy. And there's a kind of a cool story behind this. And what I think the story is that this is probably a landslide. This is a depositional event. All of the material in that valley had been washed down at the same time, which is why they're the same age. And the other half of that story is actually that fire has a pretty strong relationship with landslides. Fire has a really destabilizing effect on slopes. And so it's probably likely that about 6,500 years ago, you had an intense fire, burned up the vegetation, the slope got looser, And after the first rain, you had a landslide event, which we then sort of stumbled upon 6,000 years later. So that's pretty cool. In terms of stratigraphy, though, we have some interesting results. So these are age reversals, and this is basically a plot. We wanted to calculate the difference in age and really see which of these profiles that we sampled had younger dates at shallower depths and which ones had younger at deeper. So the negative ones are the ones where you ended up with an older date on the top of the soil profile. And so what you can see here is out of the 22 soil profiles that we sampled, about 13 of them have an age reversal. So over half actually have quite a lot of disturbance, and enough disturbance that you have younger charcoal deeper down than the older charcoal. So this would suggest that the soils in this ecosystem are really circulating much more than we thought. There's not really a stratigraphy. And that doesn't really mean that we can't use this sort of information at all to inform our fire history. But what it does mean is that you can't sample the very top surface of soil and expect to get the most recent fire. There's too much change. So in terms of history, this got rid of part of my graph. All right, so what you would see normally is, this is a Gaussian-Gaussian mixture model, say that 10 times fast. And what it has is usually it has probability curves of the calibrations of all of our radiocarbon dates. Those are not showing up, it's fine. This black line on top is the density of those curves. So essentially, this is a way of estimating site activity. So what's the likelihood of finding a radiocarbon date at that age, given the sampling that we did? And so from the mineral soil samples, which I'll highlight for now, what you see is most of the dates that we have are within the last 1,000 years. We have some going back to 4, but they're all kind of really within the last 1,000. That's a pretty interesting peak, because there's not really like a mechanical explanation for that. There's not a reason why we wouldn't find charcoal in this middle period, unless it's just that there's more fire in the last 1,000 years. And what you see too is that there's a really broad peak at 800 years ago. So that predates European settlement. And that would suggest that the Native American burning element I talked about earlier is not really being recognized in the way that perhaps should be. And perhaps there is more fire in that time period. And we need to sort of investigate why. There's also a bit of a peak in the last 100 years. That's probably more modern burning. Things like timber operations, they tend to burn slash piles, so perhaps there's charcoal inputting into our record from there. In terms of the more depositional sites, you have a really big peak at 5,000 years ago and another one at 7, with a little bit at 1,000. And so perhaps this 1,000 corresponds to what we see in the mineral soil sample record. But what's perhaps happening here is if these sites are evidence of landslide activity, then for whatever reason, perhaps we're seeing landslide activity greater in the past than we see it now, which remains sort of to be investigated. And I am going to switch gears a little bit and talk about the results from our soil sampling specifically. So these are 2 sort of metrics of soil samples. This is a pretty standard way to look at your soils. This is how dense they are. And density typically increases with depth, so that's pretty much on par for what we would expect. And then on the top there, those are the undergrad numbers. Shouldn't call them that, should I? These are the results from our physical quantification of charcoal. And so what you can see is charcoal tends to decrease with depth, but it doesn't disappear altogether with depth, which is interesting. So there is evidence that this charcoal is circulating at deeper depths and it's residing there, which is important, especially for carbon sequestration sort of talks. The bulk of it is in the top 10 centimeters, which is what we would expect, but it does circulate down. And what you also will see is there are some zeros in here, and I'll come back to that later, but that's important to know. So these are the results from our chemical digestion, or chemical quantification of charcoal, and also from our carbon analysis of these soils. So starting with carbon, these are the total carbon levels for Redwood soil. Also decrease with depth. Also, again, the bulk of it is in the top 10 centimeters, which is pretty much to be expected. And so in comparison, here's the total soil carbon compared to the pyrogenic. And you can see that, at least in this graph, it does really look like the pyrogenic carbon is a really small fraction of all the carbon in these soils. But what I want to point out is when you look at it in a ratio, what's actually important to note here is the literature gives a pretty interesting estimate for this sort of number. So right now, the review papers that are out say that the ratios of the percent of pyrogenic to total carbon is usually somewhere between 1 to 35%. So that's kind of nonsense, right? That's a huge fraction. And it really depends on the ecosystem type that you're examining. And so for ecosystems that are fire prone, they typically have ratios of 0.1 to 0.15. And so that would put redwoods right with other ecosystems that typically have a lot of fire. This is places, and we're not talking, we're talking places like Doug fir forests and ponderosa pine forests, places that have much more dry summers than redwoods, which would suggest that fire plays much more of a role in these forests than we previously anticipated, and also that they play a pretty significant role in the carbon sequestration that occurs in these forests. And so finally, these are the two results that we got for our methods of charcoal quantification. And so right off the bat, you can see the chemical method picked up more charcoal than the traditional method. And I would suggest that that means it's probably a better method, based on the explanation that we have zeros here in the physical record. And these are duplicate samples. So there isn't really a significant reason why you would have 0 charcoal in one sample and then pick up a lot of charcoal in the chemically based quantification, right? So this is probably true that this chemical method, this more newly established method, is perhaps getting more accurate results, or at least picking up more charcoal for less time and less labor, which is a pretty interesting thing. Perhaps those zeros are counting error, right? If you're looking at really small dots under a microscope and they're all kind of dark, what's charcoal, what's a rock, what's organic matter, I don't know. Perhaps that's part of the issue. Another part of it is with that physical quantification, the sieve sizes we used were 2 millimeters and 0.5 millimeters. And so perhaps some of the charcoal that we're not picking up is actually smaller than that, which is interesting. So with that, I'm going to wrap up. To revisit my research questions, what we ended up finding was we didn't really find a charcoal stratigraphy. In fact, we found that most of our sites actually had far more disturbance than that and far more circulation. But that's also important, and it doesn't mean that we can't use a charcoal record to inform our fire understanding in these places. We also found that perhaps the Native American burning element of this story is really going underrepresented, because we're finding evidence of fire peaking really dramatically around that time period. And that peak is so dramatic that it doesn't really sync up with corresponding climate records or redwood population records or anything like that. We also found that the carbon levels in these forests are really determined by the fire that goes on here, and that perhaps fire is influencing these places more than we would expect, and that maybe you don't need to hire an undergrad to do your work for you, maybe you can do it with acid. So, just to acknowledge everyone who's been involved in this, there's been a lot of people working on this project with me. Thank you, Dan Gavin, my primary advisor. Thank you to Lucas and Bart, who have both served on my committee. Thank you to Curtis Hilbert, the unknown undergrad on this project. I should probably mention my name. That would be rude. Thank you also to the Environmental Change Research Group and the whole geography. So that's it for today, folks. We've got time for
questions. Is there any ethnological evidence for Native American burning in this area?
No, not really. And my idea that actually we kind of came up with yesterday while talking to Meg, the tea speaker, was that the tribes that live directly within the redwoods don't really have sort of a history of fire. But perhaps what we're seeing is fires that occur on the eastern side of the redwoods and then are blown in west. So perhaps we need to examine also the ethnographic records of tribes who would have lived east of these places. Because if they had been burning really actively for agriculture or hunting, perhaps there's a chance that some of those fires spread easterly, right? West. I'm a geographer, it's fine.
What do we know about the settlement history when people first came in here?
I don't know an arrival date off the top of my head, especially because it kind of remains kind of unknown. There aren't a lot of sort of archaeological sites of settlements or villages or anything, especially right within these forests. There's people who would have lived probably closer to the coast, and again, probably east of this area, but off the top of my head, I'm not sure.
I mean, I guess I ask because the timing, I mean, they're not far from here. There have been people around for thousands of years.
Yeah.
So, like you said, well, that started seeing this change about 1,000 years ago. I thought, well, wouldn't people have been here for a lot longer?
That remains kind of unclear, unfortunately.
Well, it's complicated by the fact that you would expect the population to greatly diminish after about 400 years ago, 500 years ago, because of smallpox thing. And so I couldn't really tell from your figure or if other people have shown when the decrease might have happened. It was
In population?
Yeah. Well, in terms of the forest fires, like you said, it's before Europeans got there.
So that specific, I can bring that up again if that would be useful. That specific figure, this isn't necessarily a reflection of fire activity. It's a reflection of the probability of finding a radiocarbon date at that time, given the radiocarbon dates that we've got. Because the assumption here is that if you sample soils or lakes and forests, et cetera, if you sample at really random depths, we have a really wide range of depths, that you should, if fire is constant, that you should have dates all the way across here, and we don't. So I don't think this is necessarily a reflection of fire activity, but we're picking up something here. It may be fire frequency, it may be changes in how this charcoal is getting buried. Right, perhaps this is a changed ability in charcoal to get buried. Maybe there's more circulation. That sort of remains to be untangled.
I was hoping that you could talk about.
Okay, so I'll use the calls. So the Headwaters Forest Reserve was made a reserve in 1999. It's probably the last piece of old growth to get passed over into public ownership. And at the time, before it was designated that, it was considered kind of the world's largest unprotected area of old growth. And so before it was bought out by the federal government, it was owned by the Pacific Lumber Company, which was based out of Fortuna, California. It had like 3 generations of this one family who was running it. And eventually they decided, we're going to put this on the stock market. And this Texan stockbroker named Charles, I don't remember his last name, so we're going to call him Chuck. Chuck decides that if he buys up enough shares of this really small California company, that he can control he'll have the largest shareholder position, and he'll be able to start controlling their timber decisions. Because up until this point, they've been logging really sustainably. They would go into old growth and they would cut down one big tree, and that's what they would use, and they would more focus their efforts on logging in second growth, not in old growth. Because somebody had the crazy idea that if you want to have a logging company that's around for a long time, you should log as if you're going to be around for a long time. Wow. And so when this Texan buys out this company, he immediately starts to clear cut. And that was kind of his intention all along. He realized you could make a really big deal of money in that process. And so they start clear cutting. And that attracts the attentions of a lot of Earth Firster groups and other activists around the time. This was in the 90s, so you can imagine there were a lot of those in California. And so this starts about 10 years of really kind of dramatic and sometimes really violent protests. There's a story about 2 activists driving down a California road in their Subaru, because of course they're in a Subaru, and they've got kids in the back seat, and they get hit on the side really hard by a timber truck, a really big timber truck, and the trucker comes out, and the first thing he says, according to the stories, is the first thing he says is, "I didn't realize there were children in the car." Yeah. And then this all ties into, there's an activist who is involved in this whole story, who they had end up with a car bomb in their Subaru in San Francisco, and it's presumed it was the FBI, and there's all sorts of stuff. And basically all of this sort of conflict ended up with Headwaters getting bought out. And the story is the deal, they had until midnight in DC, and it was after midnight, they hadn't struck a deal yet, and somebody said, well, it's not midnight on the West Coast. And so they extended the deadline, the negotiations, until midnight on the West Coast, and finally bought it out, and that's why we have Headwaters as protected area now. There's a bunch of books about this, it's really interesting. Yeah, I couldn't put that in the thesis. But
This is how deep do Redwood roots go?
I'm not sure off the top of my head. One of the things I will point out, relatively deep compared to other trees. This is an example of a tree tip up, And I put this picture in here for a couple of reasons, but one, because this is about 2 Dan Gavins high. Which you can't see from the picture, but this is enormous. So you imagine that the root systems on this have to be pretty dramatic. And actually, the other reason I put this on here, and I didn't quite mention, is that this is probably a mechanism for that soil disturbance, or it's one of them, right? You have a tree tip up, you have a big hole, things fall in, and that's how you start to have charcoal at different depths that you would expect. So.
I'm really glad you brought that up, because if Josh Roaring were here, that's, I would imagine, I think you would say is the most important way in this kind of a forest, that soils get cycled. It's wind throw and that kind of upturn. And it begs the question about when you keep fires off and that changes the hydrology sort of thing, what that effect on how often trees fall down.
Sure.
And what that does to the soil actually change. So it's very interesting.
Yeah, I would presume that the suppression of fire in these ecosystems hasn't prevented trees from falling down, just because there's so many logging operations in a close vicinity of this, that you have a lot of big trucks coming through, you have a lot of activity, and so perhaps that's slightly contributing to that. But you're right, that is a really kind of interesting direction to start to think about what the lack of fire could do in these places. The wind rotation? Not off the top of my head. Partly because with no sort of modern record of fire within these forests, it's hard to compare that to any sort of weather pattern or climatic change. Specifically within headwaters, we have a radiocarbon date that dates about to 1996, but given that it was made a reserve in 1999, there's sort of no records we can compare that to. So there was presumably a fire in there in the last 30 years, but we don't really know the context of that. It's kind of hard to tie that into weather.
Is the problem with cross-dating fire dendro records that the insides of the trees decay, or is it that there's not enough wood line around to actually do that? Or
it's a couple things. It's the decay thing, which makes it really hard to core. But the tree rings that people started testing were usually stumps left over from logging or clear cutting. And it's been found out that if you sample too low on the stump, that you actually miss a bunch of fire scars. And so that very first, those sort of 500-year intervals, that's likely because they sampled so low on a stump that they missed a bunch of scars and underestimated pretty dramatically.
Now aren't the big logs lying around that you can actually go up a bit?
There are some. I'm not exactly sure how somebody got 500 years. That's a pretty kind of crazy result. I'd have to look at their methods more clearly, and that was probably a study where they didn't have the logs lying around because they had used them for timber. So.
Yeah, sedimentation rate or soil rate in this area?
Well, you're at the
that's
top,
okay,
right? So it's
What's that?
primarily soil production.
Yeah.
You're at the very top.
Yeah, I don't think more production. And it's not really like a lake sediment core where you can kind of track, we've had this much soil over this much years. It's always kind of being turned over and consumed. Not a lake, no. I'm not talking about lakes. Yeah.
Would you take a couple of minutes and tell us what you're going to be working on going forward?
Sure. This will make Melissa happy. There's two things. So one is related to this project, actually. We sort of accidentally ended up with isotope data for all of this. So that's going to be a really kind of interesting data set to start to explore. But specifically moving forward, I'm going to be starting on a project looking at fire and carbon cycling up in Alaska. I'm flying out Memorial Day, actually, at like 5 a.m. So in about a week. We'll be doing our primary field work. We're looking at the sort of multiple disturbance regime that happens up there, how increased fire is changing both carbon cycling and permafrost, and all that sort of things in the boreal forest in interior Alaska. And I'll be based in CU Denver in their integrative biology department. And the plug for that is Denver will be hosting AAG not next year, but the year after. So I can probably find a futon in between now and then.
So, thanks, Kate.